Hello, everybody. Oh, good, you can hear me. I was about to say I'm Texan, but I'm not that loud. So today, we're going to be talking about transfer learning. So if you're intending to be in a discussion about fashion, you're in the right place. And if you're not, I will not feel bad if you flee the room to go watch Mark Zuckerberg be very uncomfortable in front of Congress. So my name is Paige Bailey. I do things with computers. I'm currently doing things with computers at Microsoft. So I've got about 10 years of experience with Python and about 5 years building predictive models, first with machine learning and most recently with deep learning. I'm based out of Redmond. I work for Microsoft, so that kind of makes sense. Don't throw tomatoes. I'm under the impression that most people here are Windows folks, though. Like, how many people use Windows at work or in their personal homes? Wow, that's awesome. I don't, mostly. So today we'll see Windows a little bit, but then we'll be bouncing to Ubuntu. So is anybody else a fan of Linux here? Word. Awesome. So, and also feel free to tweet things. I'm on Twitter, dynamic web page. I love puns. Feel free to also send me puns of my name. And yeah, so with that, let's get started. So today is going to be a little bit of an overview to begin with. So a little tiny bit of theory, but there will be code, so don't be afraid. We're going to start off with what is artificial intelligence. Then we're going to talk about what is deep transfer learning, so conceptually, what is it? And then we'll be going through a case study where I will be building out an app from the Clueless movie, which is probably dating me a little bit. But hopefully there are not, like, I assume there are some people here who were born recently. Clueless is a movie that was very popular in the 90s. So you should go see it if you haven't. So to begin with, what is artificial intelligence? And artificial intelligence is really any technique that enables computers to mimic human behavior. And if you go by this definition, artificial intelligence has been around for a long time, ever since Turing machines were in existence, right? Like it's basically anything that you could give an if-else statement that sounds like a human. You know? So artificial intelligence around for a while. Machine learning, also around for quite some time. Neural networks have been around since the 60s, or at least the basic building block components of neural networks. The United States Postal Service has been using neural networks to detect handwriting on envelopes since the 90s. So again, been around for a bit. And it's the ability to learn without being explicitly programmed. So who here is in the business of building out predictive models? Like that's what you do for a day job. Cool. So when I worked for Chevron, so that was the job that I did before I came to Microsoft, they were very devoted to traditional vanilla machine learning models. And that was mostly for the capability of doing auditing, right? Like it's very easy to point at a machine learning model and say, well, you know, my decision tree said do A and then B and then C. So if you're going to sue me, like I have a very clear path as to why I made that decision. And they were very wary of looking at deep learning because it's a little bit more of a black box. Like you can tell when it's learning higher level features, but it's very difficult to actually say, oh, well, it saw very long cat whiskers, and that's why it thinks a certain way. But for folks who didn't raise their hand, a basic overview of machine learning. So you either have labeled data or you don't. If you do have labeled data, lucky you. You know, it's more of a straightforward process. You can do something called supervised learning, and that's either classification. So you're either predicting, oh, that's red, that's blue, that's a cat, that's a dog, that's A, B, that's Republican, Democrat, you know, some sort of category. And you could use something like a support vector machine. You could use decision trees. You could use, regression trees, lots of different algorithms, hundreds, thousands. And if you're trying to predict a numeric value, that's a regression task. So I'm going to sell 6 widgets next July. It's going to be 52 degrees next Wednesday. That would be more of a regression. If you don't have labeled data, then your life is going to kind of suck because you have to do unsupervised learning, and that's a little bit difficult. You have to do things like clustering. You don't know the answers ahead of time. You have to have some sort of domain-specific knowledge or some intuitive guess as to what kind of clustering makes sense. And that usually takes a bit of time. There was a tweet I saw recently that instead of spending 6 months doing unsupervised learning, what you should really do is just pay an intern to classify things for a month, and then you have a supervised learning task, and that makes life a lot easier. And I subscribe to that. So I think that you should absolutely try to do supervised learning anytime that you can. But that's a lot of words on a slide. Doesn't really make sense. So let's try an example, right? So say your boss gives you a CSV file, because it's always a CSV, and it's our customers.csv. And you work at a bank, and your boss says, all right, we have some information. We've got their ages. We've got whether or not they have a job, whether or not they own a house, their credit rating, their education, and whether or not they defaulted on a loan. But really, if you're my boss, all you care about is that last column, right? And really, all you care about is what is the likelihood that this potential new customer who is 35, who has a job, who doesn't own a house, who has a bad credit rating, who did go to college, what is the likelihood that this person will pay us back or not? And what you can do is you can build out a decision tree. This is an example of one of those classification algorithms that I was telling you about before. And each one of these nodes will have a question that you're asking, and based on the answers to those questions, you traverse through the tree, and then you wind up at a result. So if we go through what we had for our potential customer before, we've got yes, he looks like he's not a substantial risk, and we should give him a loan. And usually what you would get back from that decision tree would be a classifier, so yes or no, or loan or not, and then some confidence level. And again, it's great to have theory, but it doesn't really matter if you don't have code. So if you go to this URL right now, and I'll leave it up for a couple of seconds so that folks can take a look. I've got every single piece of code that I will be showing today in an Azure Notebooks repo called AnacondaCon 2018. It looks like everybody can see it, so that's great. So if you go to that first, Jupyter notebook, you should see an IPython, or it's an R model built to do precisely what I just described. So it's taking a credit data set from UC Irvine because that's where they, this is the one that everybody uses because UC Irvine has a ton of great data, very straightforward alphanumeric data sets. And you pull in your CSV file, you get a bunch of features. So each one of these things with a sigil would be considered a column in a data set if you pulled it in. And it's all of different types. So you have some factors, some integers, and each of these kind of gives you a different facet of what each customer would be. If you see DM, that stands for Deutsche Marks. So they're how much money they have in their bank account. So you pull in the CSV file, you get some information about the different quartiles. You decide what, after you randomize the data set, you decide to divide it into training and test. This is abnormally biased towards training, so I've got 90% in training and 10% in test. Usually it's more like 70% training, 15% validation, 15% test if you're doing typical machine learning. And then you train a model. And to train a model, all you really have is that one line of code. So we're using a C5.0 decision tree. We're using all but that last column because that's the answers, right, whether they paid us back or not. And we're building a model based on all of the other information that we have on those customers. So we're trying to predict that last thing, and we're basing it on all of the other variables that we have at our disposal. So you build out a model, and once you do, it gives you a whole bunch of information and a decision tree that looks less pretty than the one that I put on my PowerPoint slide. You go down, It tells you your error rate, your confusion matrix, so how many you correctly classified and how many you didn't, and then the attribute usage, so which of those features was the most predictive. And it looks like checking account balance was what it decided on. If you want to make this model even better, you can start stacking decision trees together. And once those decision trees have been stacked together, so here I went through 10 iterations as part of a boosted decision tree, and you can get an even better idea of that attribute usage and your percentage correct. So that's great. And that's an example of what you would do if you were going to be doing machine learning. But machine learning is kind of problematic, though, right? So there we go. So machine learning is kind of problematic. And part of the reason, think about it. We had a very clean CSV file that we pulled in. We had only one iteration of an algorithm that we tried. And that's not a very realistic situation. Like the stuff that happens in textbooks, and that is a very textbook case, never happens in real life, right? Your data usually looks more like this. So, your features aren't standardized. You have strings where you should have numeric values. You have long ints and short ints in the same column. And it usually comes in a variety of sources. Right? So sometimes it's CSV files, and it feels like everything is CSV files sometimes, like CSV files stored in like 12 different machines. Some of the time it's XML files that you have to parse out, or JSON that you have to do something similar, or Hive tables, or databases. And sometimes you have to hunt down other features. So we saw there that the account balance was one of the best predictors as to whether a customer would pay us back. And that wasn't something that was included in the original data set. So you, as a data scientist, would have to go to your boss and say, hey, let's try to track down that information and see if we can find it, because I think it would be a great predictor for my final model. And so the thing that I want to hammer in is that traditional machine learning can be extremely effective on alphanumeric data, and that it requires less hardware than deep learning. So you saw there I was using just a CPU in a browser, on an open platform. But it also requires a great deal of work up front. So you have to get data into a nice structured rectangular format. You have to clean out the nulls and NA values. Some algorithms don't really like to play nicely with those. You have to understand that if all of your null values happen to concentrate around a given month, so if you check to see that you might have 12 nulls, but they all fall in September, do you want to build synthetic data, or do you want to just kind of guess that maybe those September values would be consistent with August and October? So it's a lot of work that you have to do, a lot of feature engineering in order to make those models more effective. So we talked about artificial intelligence as kind of the broad overarching term. We talked about machine learning. And for the rest of the day, we're going to talk about deep learning. And this is the thing that happens to be vogue in MIT Tech Review or whatever the heck. And it's learning underlying features in data by using deep neural networks. What does that mean, right? So artificial intelligence with deep learning is used in a variety of ways, primarily in images. And this is what gets people most excited, or what tends to get people most excited. So you submit an image, and immediately all of the different underlying features are detected. So you send in a picture, and it detects that there's a dog, a person. If I took a picture here, it would detect that I was taking a selfie in front of a room of people. It can detect specific people. So automatically unlocking my laptop whenever it sees my face. Or cancer detection, right? So if you have a number of X-rays that are labeled cancerous and non-cancerous and placed into two different folders, you can train a deep learning classifier to figure out whatever constitutes a tumor in those lungs. There's also text. So if you feed a deep learning algorithm all of the text from Harry Potter books. It comes up with Harry Potter and the portrait of what looked like a large pile of ash, which does sound like something J.K. Rowling would write. But yeah, so it's basically just being able to build out something that sounds like natural language coming from the brain of a human. Also sound, right? So Google has a project called Magenta that makes music using machine learning, and it's actually very listenable. There's also some music that's been auto-generated in the last couple of years that is not listenable, but would be called music. And then also speech to text. So you see there Andrew Ng, when he was working for Baidu, talking about taking speech, translating it to text, and then doing text in one language to another language detection. And a whole heck of a lot more. It feels like every day there's a new use case for deep learning, and it's all revolutionary. It's all something that's, breaking into a different domain and going to be completely life-changing. Right? So there you see a few more examples. Starry Night kind of juxtaposed on top of Mona Lisa. AlphaGo, which are two generative adversarial networks, two neural networks kind of fighting against each other in order to win the game. Automatic detection of cars and sort of self-driving footage, and the list goes on. And the reason deep learning is becoming so popular recently is because it's more accurate than humans now. So has anybody heard of Andrej Karpathy? I assume yes. Yeah, a few hands. So he's the head of data science at Tesla. He used to be the head of data science at OpenAI. And what he did as a grad student was he sat down, and over the course of a few months, he hand classified every image in one of the world's largest training data sets. So this is what I imagine. I can't really imagine that he had a great graduate school experience. Like it must have been very sad and kind of pathetic. But actually, man, this is being recorded. I'm sorry, but no, Andrej Karpathy's awesome. But he was termed kind of the human benchmark for image classification because he was 95% accurate. This is a cheetah, this is a parrot, this is a car, this is a truck, that sort of thing. And in the last few years, neural networks have surpassed Andrej Karpathy's benchmark for accurately classifying images. Neural networks are now also better at translating spoken word and text to other languages than humans happen to be. And they're better at detecting voices from a large number of people in a room. So if all of us started talking all at once, I would have a lot of difficulty picking out a person from the back of the room, whereas a neural network would be able to do that very quickly. So another reason that deep learning is becoming popular recently is because specialized hardware allows us to train large amounts of data in less time. We've got a ton of data now. It wouldn't have been feasible to train about a decade ago. So we've got FPGAs, which is Microsoft's chosen solution. In the next couple of months, you should see a pretty exciting announcement about that. You also have things like GPUs getting more vamped up. Today we'll be using a Tesla K80. And then also things like custom ASICs. So algorithms that are actually burned into the silicon on the hardware. So if you've heard of tensor processing units, that's one of the examples of custom ASICs. And there are many more. So if you have a favorite algorithm, that you could get better performance by actually building out custom components yourself. The drawback of that is that if you have a custom ASIC, it's not as easily transferred for another algorithm. So if I'm using TensorFlow, TPUs are awesome. If I'm using a different framework, then TPUs might not be the best choice. And like I said, we've got a ton of data. We also have great open source technology. So TensorFlow would be an example. Also MXNet, CNTK, a bunch of other deep learning and machine learning frameworks are open sourced. So getting started with artificial intelligence, you really have two options if you're going to be doing deep learning. You can either build your own model from scratch, or you can build off somebody else's. So let's start with why you don't want to create your own model, or you want to avoid it at all costs, right? So if you're building a convolutional neural network, it looks something like this. So you have an input image. It breaks it down into smaller subcomponents, smaller feature maps. And through each layer of the process, you're learning more and more granular features of the image. So what does that look like? If we have a picture of a car, and this is from a paper from Zeiler and Fergus in 2013, you start learning low-level features. So these edges that you see in that first segment of pictures. Then you start learning mid-level features, so things like hubcaps and edges of wheels. And then you start building out a more trainable classifier, so it actually understands what a car happens to be. And if you look through examples of layers, you can see that in practice. So eventually, you start breaking down into more and more granular features. And if you look in the top left there, you can kind of see that instead of, it recognizes that it's a dog. That was something that it learned in one of the lower level feature layers. But when you get to the higher level features, it's actually starting to detect, okay, well, which are Cocker Spaniels and which are Beagles? And even though these look very similar to humans, how can I, as a neural network, differentiate between all of them? And then at the end of it, after all of these back propagations through layers occur, you end up with a classifier. So this would be a classifier for a car, and it would spit out Audi A7. The crux of it, though, is that creating your own model would take time. It would take a ton of data. It would take experienced engineers, and it would also take extremely specialized hardware that's also very expensive. So time, that's to the order of weeks or months. If you're going to be training some of the data sets that Google does or Amazon or Microsoft, it is on the order of weeks or months. If you need data, it's often millions of classified inputs, sometimes billions or trillions. Experience, everybody wants to have a data scientist with 5 years of experience, but that hardly ever happens. They're very hard to find in industry. And hardware, again, you would want GPUs, TPUs, FPGAs, something of that nature, and those are also very, very expensive to train on, especially if you're going to be doing it on a cloud infrastructure for weeks or months at a time. So all of that, not exactly the best business case if you're trying to convince your boss that you should be doing deep learning. But if you want to modify somebody else's model, that takes less time and less data and less hardware, which sounds kind of magic, right? That's, I'm interested now. And this is where we start breaking into the actual project, right? So for the first step, you have to have a challenge, right? So you have to have some sort of research question, some sort of meaningful life proposition that would make your life easier. And I suck at clothes picking. I am super bad at it. I am not good at all. So this is actual documentary footage of me trying to find things in a closet. And there's a movie that I loved when I was growing up called Clueless, where Cher magically had this thing on her in her bedroom that had pictures of all of her clothes kind of downloaded to it, and all she had to do was flip through, click dress me, and it would tell her, oh, that's a bad life decision. You should not be wearing that. Or you cycle through it again, and it works out the way that it should. So I want to build that. I want to build a best friend to tell me when I'm making poor choices. That is what I want to do. So we're going to attempt to do this with transfer learning. So framework selection, right? I mentioned before that there are a number of popular machine learning packages. There's scikit-learn for Python, there's Caret for R, and a whole slew of other algorithms for R for doing machine learning. So we saw one before, C5.0 for decision trees. But they're not really what we need, right? So scikit-learn, R's libraries, they're not really intended to be for deep learning. And for deep learning, you have a number of open source frameworks to choose from. But the hallmark of a great framework to select, I feel, is always how many quick starts can you find, how many tutorials, how many walkthroughs, and how much code can I copy and paste from Stack Overflow. And, and in terms of all of those things, TensorFlow wins by a landslide. 95% of deep learning projects are built using TensorFlow. It has a number of great example use cases, including one specifically for transfer learning, and that's the one that we'll be tweaking today. So step 2, algorithm selection. And this is going to be dictated by what data you have available. I don't have billions of images of clothes. I'm not that kind of a person. I maybe have hundreds. Your research question, your business requirements, and more. But like I said, we're going to do transfer learning today. And transfer learning is a machine learning method where a model developed for a task is reused as the starting point for a model on the second task. So what does that mean? That's a definition taken from a textbook by Ian Goodfellow and Yoshua Bengio, who both happen to be out of the University of Montreal. Now Ian Goodfellow works for Google, and Yoshua Bengio kind of does contract work for Microsoft. But what does that mean? It basically means that you chop the last more high-level feature aspects of a model off and rebuild it with your own little Lego blocks. So I know that there was a talk yesterday that mentioned transfer learning kind of theoretically, maybe not so specifically, but it's training the base model. So training your base model on massive amounts of data, again, takes time, it takes hardware, it takes lots and lots of data. Transfer learning usually takes minutes, and it often doesn't even require a GPU. But we're going to use a GPU today. And just to prove that it takes minutes, let me pull it up and start. So this is, has anybody ever used X2Go? That's a no. That's a resounding no. Wow. Okay, cool. So homework for today. Go and look at X2Go, especially if you're using Ubuntu machines on a cloud environment. It provides a desktop interface to them. So this is me logged into an Ubuntu virtual machine on Microsoft Azure. And I'm going to be running a training TensorFlow model, specifying some outputs, and then also where I should stick my retrained labels. So let's see if this still works. Perfect. Perfect. It's creating some bottlenecks. This looks like good text coming from a screen. And eventually, let's just make sure. Let's take lots and lots of bottlenecks. It's creating one for every single image that I'm using to train. And we'll explain what this is cycling through in a little bit. There it goes. Okay, cool. So you can see here that I'm starting to train. I'm building different steps in the process. It's going through training accuracy, cross-entropy, validation accuracy, and you should be bringing the cross-entropy down over time and the accuracy up over time. So cross-entropy down, accuracy up. And we're gonna monitor that as we go through. But back to the PowerPoint slides, right? So takes minutes, I promised, or else we're going to be here for a while, and in which case I apologize. And it often doesn't require a GPU, but this guy that I'm training on does have a GPU. So it's kind of like learning immediately, right? Like you're training based on low-level and mid-level features that Google or Facebook or Microsoft, out of the goodness of their heart, created a model. It took them months. They trained it on millions of images, and then they open-sourced it to the world so that we all can build off it and hopefully contribute back to the deep learning frameworks. So Andrew Ng If any of you have taken his classes on Coursera, I highly recommend them. They're fantastic. He said in his 2016 tutorial at NIPS that transfer learning will be the next driver of machine learning success. And really, I operate in a business. What I care about is the viability of it. So what kind of commercial success will we see? And right now, most of our commercial success is coming from those machine learning projects that I did back at Chevron that are still so very popular, that are decision trees that have been built out over time. And those are very commercially viable. But transfer learning is also anticipated to have increased success. And supervised learning, not a lot of research. Even if you go on arXiv, there aren't a lot of papers being put out about unsupervised learning breakthroughs. It's mostly just new breakthroughs on supervised learning. So that's cool. We chose our algorithm, we launched it, and hardware requirements. So that would be step 3. And I have a thing called cloud privilege. And this is a term that was coined by Jesse Frizzell on my team. And it basically means that I work for Microsoft and I get to use Azure things for free. So I'm going to use lots of Azure things because they are free. Everybody else, you can use your own personal desktop. That's fine. You can use AWS. You can use GCP. You can use Heroku. I don't really care. Use whatever you feel most comfortable with. But what I chose was a deep learning virtual machine because that's what I have access to. And the specs are what you can see here. So I have 6 vCPUs, 56 gigabytes of RAM. I have a Tesla K80 graphics card, lots of hard disk space. And the way that you would go about provisioning it would just be to go to portal.azure.com. Please do not judge me for my clutter. You would create a resource. You would look for deep learning virtual machine. You would click it. And it would give you the option of creating one in Windows and I believe Ubuntu 16.04. And there might be a CentOS version too, but I don't know anybody who likes CentOS. So you could pick whichever flavor you feel most happy with. Cool. So we chose some hardware. We chose an algorithm. We have a research problem. I already did the live demo, so we're good there. Let's talk about why GPUs are so well suited to deep learning as I stall for time while my model completes. So why would we want to use a GPU, right? CPUs are designed for very generic workloads and very sequential workloads. GPUs are designed to compute in parallel the same sort of thing over and over and over again, right? So that fits in really, really well with that structure of deep learning algorithms that I was showing you before, right? With those layers that are all kind of doing the same exact thing. They work really, really well with GPUs. GPUs also have higher bandwidth to retrieve from memory. And applications that require image processing, so for example, the convolutional neural nets, they have GPU graphics capabilities can be exploited to speed up those calculations. So the takeaway there is that you have high speed for CPU, but lower efficiency because you're doing kind of things sequentially instead of all at the same time. And GPU have high throughput because you're doing lots of things all at the same time, even though they're the same thing, and higher efficiency. So another reason to use a GPU is, like I said, so pretty much neural networks, the layers all are computing the same task over and over again. And even though there are only 3 layers there, the number gets up into the hundreds, right? So you're probably going to have pretty deep neural nets if you're using TensorFlow to train something quite complicated. GPUs are also most successful at doing those large-scale models that I mentioned before. So the model that we're using is Inception version 3 on ImageNet. ImageNet is 14 million images that have been classified. And the performance over time for people who use a GPU, it just gets better and better. So that would be another reason too. Some disadvantages: memory capacity on GPUs are lower than CPUs, and the highest known GPU only contains 32 gigs of RAM. CPUs are required to transfer data to the GPU card, and that's usually takes place in a PCIe connector, so that little thing that you see there under the R. And that's much slower than CPU or GPU memory. And GPU clock speeds are also like a third of what you would get for GPUs. So sequential tasks don't really perform very well. So if you don't use a GPU, what would you use? And that would be FPGAs or custom ASICs like TPUs that I mentioned before. But unfortunately, those really aren't available on any cloud right now that I know of. So I know that, like I said, Microsoft's chosen solution are FPGAs. Google recently sent out a survey that was very, very long. It was like 30 questions and very detailed, asking you specifically which algorithms are you using, and please link the referenced academic paper for them. And I filled out 5 of those surveys, and with different email addresses. Most of them did not have page.bailey at Microsoft. And you know, most of it was just like Page.Bailey, the open source contributor. Page.Bailey, the person that is not going to use this for evil purposes whatsoever. But I still have yet to receive a TPU. So still waiting on that. But hopefully those will happen in the future. If they do, then it'll give you even more speed than traditional GPUs. FPGAs require a little bit more work up front because they're not specially suited for any particular algorithm. TPUs specifically suited for TensorFlow. So that's the hardware piece. Data sourcing. So I mentioned before that you don't need as much data if you're going to be doing a transfer learning model. How much data is not as much data? So you'll need at minimum 100 examples for each transfer learning category, though if you can sometimes get away with a little bit less, but 100 examples is a good rule of thumb. And again, that cloud privilege thing, I work for Microsoft, and we have this thing called the Bing Image Search API. So instead of going to Google, typing in pretty flowery dresses, and right-click save as all of those JPEGs, I'm just going to use the Bing Image Search API. And what that does is it allows you to search through a search engine. You can specify whether you want public versus private images. You can quickly query based on whatever plain text you want. You can specify dimensions, resolutions, extension types, so whether it should be a GIF, a JPEG, a PNG, or whatever. And then you can also select different aspects of metadata and different geographic locations. So there's a big slew of stuff in the API documentation that you can search on. And the amount of code that it takes to do that is really this. So it's less than 10 lines. You import a bunch of libraries. You specify what your search term should be and what the parameters you're searching for are. And then you get back as many images as you want. So I wanted 100, and I got back 100 for each of my specified categories. And then for training, I mentioned before that we used Inception version 3. So that's trained on ImageNet. Again, 14 million classified images. And at least 1 million of the images, there are specific bounding boxes, which means they are even more accurate. It was open sourced by Google in 2015. It's available on Kaggle's website. I highly recommend that you go and download and play with it. But if you don't want to, there is a model zoo from Caffe with very highly specialized tasks. And again, all of these are linked in that main repo that I have here. So if you want to take a look at the Caffe Model Zoo, here it is with all of the models that are available open source for free and all of the supporting papers that give you their error rates and also what kind of images they were trained on. So if you want to play, you have a lot of stuff to play with, and that's awesome. So going back to the slide deck. Word. These are also very image-centric examples. There are a lot for other specific use cases. So if you don't want to train on images, you want to train on sounds, you want to train on text, there are things available for you too. Word2Vec is really good for language, and so is Stanford's GLOVE model. Highly recommend both of them. So conceptually, what a transfer learning model is you have that main big model that took weeks or months to train. You have millions of images that were used to train it and their output labels. You take the learned knowledge, you kind of Lego block on your own modifications with your small number of images and your small number of labels, and then you go into testing. So let's see how we're doing. And going back, oh, cool, we finished. So that's awesome. So we ended up training our model. Our train accuracy got up to 100, validation accuracy around 92%, which is pretty dang good. And it gives us a little bit more metadata about it. But let's see what kind of data that we trained on. So as you can see here, I am not only a fan of 90s teen movies, I am also a fan of 80s teen movies. So we have here the jock, the basket case, the princess, the criminal, and the nerd, which if any of you are a fan of The Breakfast Club, I hope you get. For people who are born recently, I apologize. And so what I had done was, like I mentioned, I went through and I scraped a whole bunch of example images for flowery dresses, for other different things, and it popped up with, this is kind of a princess outfit. This is a career woman, that sounds very severe, outfit. Casual brand women. Yeah, that's very feminine. Cool. So lots and lots of example images there. For the basket case, I didn't really know what to put, so I just ended up, let me go back. So I just ended up getting like tiger onesies and like Halloween costume type things. And Star Wars Chewbacca. What does that look like? Oh, there we go. He looks so proud of himself. Look at him. Good job, dude. But yeah, so that's what we ended up training on. And let's try this. So those images are what built our model. And if we wanted to test it, this is my test image that we're going to be using to train our classifier. It looks very princessy to me. Let's try it. And all I'm doing here is taking the labeler.py file that you should be able to see in the repo, which it only specifies that I'm taking one of the arguments after it and using that as the input image, and it kind of initializes my model and runs it. Let's see what it has to say. And it's running with Python. It's giving me some error messages. And it's also saying, yay, princess score of 99.9% confidence. It might be a little bit of a basket case at 0.039%, and just a little bit nerd, just a little bit jock. So my classifier seems to be working with that one example. And that's pretty cool. If I want to get some insight into the performance, let's see. If I want to get some insight into the performance, I can launch a thing called TensorBoard. Have any of you played with TensorBoard before? If you haven't, I highly recommend it. So it's also one of the offerings that comes with TensorFlow. And if you bring it up, you use localhost 6006, and what it gives you is kind of insight into what your model is actually doing through each one of its iterations. So you can see your performance over time. It can also create a graph for you to see what kind of higher level features it's learned, what the lower level features are, and what the different aspects of the model happen to be. So if I zoom in, whoa, that was way too much of a zoom in. it goes through, and each one of these little aspects is interactive. So that's nifty. Perfect. So going back to my slide deck, classifier seems to be working based on 100 examples for each of those categories. We deployed it and we visualized it with TensorBoard. This is an example of TensorBoard, inferencing on a larger, much larger data set. I believe this is the one that Google has for Inception itself. So if you ever wanted to see what it looks like to classify 14 million images, it looks like that. And it goes through and it kind of mentions each aspect of the process. For deploying the model as a REST API, again, this feels kind of like cheating, but I have cloud privilege. And each aspect of this technology is open source. So Python's open source, Docker is open source, kind of launching it as a web service and then creating a REST API for it is it's fine. If you're using Azure Model Management Service, you can also do it for free by yourself by using Flask. So doing Flask plus Docker, you can deploy as a REST API. It would just be a little bit less straightforward. But if you go through, you take your model, and it would be the same if you had a scikit-learn model. All you would do is specify a schema.json file for your inputs and for your outputs. And for my inputs, it's just the path name to an image or the URL to an image. And the outputs would just be those 5 classifiers and confidence levels associated for each. And those would be exported as a JSON blob. So you would have that schema.json. You would have a score.py file that has an initializer function for your model. So you would initialize the model. You would run it on whatever your input happens to be. You would bundle all of that up as a Docker container. You would register it on Azure if you decided to use Azure Model Management. Or if you were going to be doing it with Flask, you would follow the TensorFlow serving recommendations, except instead of using gRPC, you would just use Flask as your client side, and then that would be it. And the way that you would call that web service is here. So that's the code. You would register it with an API key, and let's see if I've got it. Cool. And I might have to unplug for a second because I'm not sure I removed my API key. And even though I love you all as human beings, I really don't want you to beef up all of my charges so my boss gets upset with me. So let's see that. Yep, that was true. So let me scroll down a little bit. Oh, cool! It's reminding you that there's a party. That's a great thing. So here we are. So the keys are hidden from you. Excellent. And all I would have to do is run this, or wait, and there are the keys. Never mind. So it looks so. So I am going to delete this immediately after this presentation is over. So but there you go. So JSON blob, very confident that it's a princess. Let's take a look at what that image happens to be. As we scroll over, Control-C, Control-V. Yes, leave. Yes, I understand. I made a bad life decision by leaving the API keys exposed. So this is the one that I tested on, and that does look very, very princessy. So my web service also works as deployed by a Docker container. That's cool. And so the other thing that I probably shouldn't mention is I basically just told you how to create one of Azure's cognitive services, which are I gave you an open source way to recreate a cognitive service. So but still, you should totally buy cognitive services from us. Because it's much easier. And using model management, I believe there's a cost associated with that too. But yes, so if you want to learn more about transfer learning, I was told by the head of the team that this is the way to enlightenment. TensorFlow Hub was recently announced at the TensorFlow Dev Summit. And basically, it's an open source online marketplace where you can share not only pre-trained models, so those big old honking things that we were using to base our model on, but also model components. So say I built out a model that got really good at recognizing cherries or something, and you had a model that you also wanted to recognize cherries. You could take that higher level feature component and stick it into your model. And it would work just as easily. So if you have interest in that, go to tensorflow.org/hub, and there will be a number of resources for you to get started. If you want to learn more about artificial intelligence, and I realize I'm at time, there are a number of resources that are really bad, like lots of resources that are really, really bad, but some aren't. And Andrew Ng's Coursera courses, both of his specializations for machine learning and deep learning are fantastic. DataCamp, also fantastic. The MIT OpenCourseWare Introduction to Deep Learning that was a week-long curriculum was great. It was spot on, 8 videos on YouTube. I recommend Kaggle, the Azure Notebooks examples, TensorFlow Playground. And then also, please, this is a big, big thing. Take a survey, please, for me. If you enjoyed this, it's based on Azure Notebooks. And there are a number of bosses in this room who would be, or at least I hope they're in this room. If they're not, don't pay attention to what I said. But seriously, though, please take the survey. I'm Dynamic Web Page. I work for Azure. That's my team. They are amazing. And thank you so much.